To introduce today's next speaker, Bolys Sabitbek from Queen Mary University of London, and he's going to talk about global existence and non-existence of semilinear wave equation with a new condition. So, Bolys, when you want to start, go ahead.
Thank you for organizers to organize this workshop and inviting to as a speaker. I'm pleasure to speak. So I'll talk about global existence and non-existence of semilinear wave equation with new condition on nonlinearity. But other way is like kind of use a potential wells method to prove this semilinear wave equation. So content of this talk will be first is introduction, and in introduction I will set the problem, and I will discuss this new condition on nonlinearity and give some literature overview, very brief one, and I will give a main goal of this talk of this work. Second, I will introduce potential wells theory or method by giving some simple example and giving some other properties. Then by using this potential wells method, we can obtain invariant sets and vacuum isolating of solutions. Then we can prove global and Blowup solution to semilinear wave equation. Semilinear nonlinear wave equation. First here, we prove that for initial global solution for initial energy less than depth of potential well, and when it's equal critical case, and this case we will have a global solution, and when is a initial condition, initial energy is negative or less than d or equal critical case d, and Nihila functional positive negative, then we prove the Blowup solution for semilinear wave equation. First, setting of the problem. So we consider the initial boundary problem. So we have here in semilinear wave equation with this kind of nonlinearity. Our Cauchy condition, initial condition, then we have a Dirichlet condition on boundary, where omega is bounded domain in Rn. So we have total energy of this problem for this form. So I mean here is a notation 2, it means L2. So it's, and we have this kind of Fu and minus some constant. It is positive, it can be 0, but we keep as just positive constant. And big Fu, it has this form. So when is we have take derivative, differentiate with respect to u, we get just Fu here. So condition on nonlinear term. First, we will have an f from S1 and f at 0, and the first derivative at 0 will be 0. Second, we will have a inside will 2 form, whereas the f is a monotone, and it's convex for when u is positive and concave for u is a negative. So we consider here real valued function u. And b is f is the convex for all u between minus and plus u, infinity. Third is that alpha is bigger than 2, and it's less or equal to than gamma, and less than this term. This we have this condition because we will use embedding theorem. That's why we have less than this one. So then we have the growth condition on growth that UFU less than omega gamma from this side, and other bound from that alpha is fu less than u fu and beta u plus alpha some sigma. Whereas the beta is between 0 and lambda 1 alpha means -2 divided 2, whereas lambda 1 is the first eigenvalue of Laplacian. So this condition we denote as just h. In this case we can say is HA, and for this case we say is HB. It's in some point it will be a little different. We need some assumption when we prove HB condition. So now we have some property of this nonlinearity that let fu satisfies h previous condition. Then in the HA case, when it's convex for positive u and concave for negative u, then we have fu is positive when u is positive, and it's obvious, okay. Fu is negative when u is negative, and fu is non-negative, and big fu is non-negative for this interval, and big fu is increasing when u is positive and decreasing when u is a negative interval. For HB, when is convex for from -infinity to +infinity interval, then we have that it's non-negative fu for this interval, and ufu is positive, and if big fu is positive for u is positive and is negative when this term. So, and big fu is increasing in this interval. But you can see here from this term and h and b is a little opposite to each other. You can see from here, if you compare, because here is always positive for all the interval, but here it's negative when u is negative. So we some point we use this kind of small properties of the nonlinearity fu. So I would like to give a little brief history of this nonlinearity, some condition on nonlinearity, which I see will be interesting to see that this kind of condition for growth condition that 2 plus some epsilon and big fu is less than u and fu, and this was first introduced by Levin and Pioneer in 1974, but in the abstract form, where they put for Blowup solution from abstract parabolic equation. And Philippine Protecheva, they proved this they give this exact form, and they used to prove for heat equation, Blowup solution for heat equation, and this was improved by Bandl and Brunner 98 in this following form by adding some positive constant sigma. And also this recently it was extended more for adding this term, and it was introduced by the Korean mathematicians Chung and Choi, also for heat equation. And we with Professor Żański and Sabitbek, we use this condition to prove Blowup solution for porous medium equation. So what's the difference between this condition is that this include all of these equations. Also, this condition is depends on domain due to this beta. You remember that the beta is dependent to first eigenvalue. So, and first eigenvalue is dependent on domain. So when the domain is large, first eigenvalue is small. So it will be close to, if the so big a domain and less will have small first eigenvalue, and this term, this condition will be same as this one. But if domain is small, then first eigenvalue will be large, and we'll have this one. So we'll have this kind of connection to this condition to the domain. So it's kind of very interesting concept to see. In overall literature review is as a semilinear wave equation is very big. They have a huge literature on this term in the different direction. It's impossible to say or mention everything. So here I will give only one direction of the how to prove the global and global solution and Blowup solution. So I will just first mention early works by Keller, Sattinger, Jorgensen, series of Tsutsumi, and some work of Levin. And first is in 1975, pioneer Sattinger introduced potential well method with condition H, but with where the beta 0 and the sigma when is 0. And is introduced from heat equation and the wave equation. Also, they they used for wave equation and heat equation. Then recently, 2006, Chinese mathematician Liu and Zhou generalized and improved this pioneer Sattinger's results by giving some invariant set and vacuum isolating of solution, some threshold results for global and Blowup solution. So they improved a lot essentially to this work of the pioneer Sattinger, introducing also the family of potential wells. But they proved for only for HA case. But in 2010, Zhang Xiu considered the critical initial energy. So he proved all these results for critical case to critical initial energy when the initial energy is equal to D, depth of the potential wells. And Zhang Xiu has more works on proving this using this potential well method to parabolic, pseudo-parabolic equation and some other works. And recently Chen and Chen solved for case H in equal HB condition, and they filled this gap for this direction. And my goal of this talk or this paper, which I has a preprint. So again, we consider this initial value, initial boundary value problem with assumption for H and HB, we consider both as in pioneer Sattinger work. We introduce to HA this new condition from Korean mathematician Chang Choi, where beta between this term, so it has depends on domain. And all using these terms, we prove potential wells theory, and then we get invariant set, vacuum isolating of solution, some threshold result for global existence and Blowup. So again, we prove that for initial energy less than D and Nihila function is a positive, global existence. And when the critical case, initial energy is equal to D, and here it should be positive or non-negative Nihila functional. For Blowup case, we prove that initial energy less than D again, and Nihila functional is negative. But here we can include also the negative case. Here, initial energy should be always positive. For critical case, we have same, but we need more additional term that initial conditions should be, the integral should be positive. So, but here we cover all these results in one paper, and adding more this condition. So we cover most of the works. So now I will talk about the potential worlds theory, which for me is a very interesting method to see in different angle to perform global existence and Blowup solution, and it has a very good intuitive thinking. For example, imagine that one-dimensional mechanical analogy of our problem. So we can write in this following form, and it has its potential energy has this following form. Again, fx is this form. Then we can have, actually here is energy, and this term, it will be this curve for potential energy. Then we have a local minimum at 0 and local maximum at x1. So x1 is, here we will have this d, depth of the potential wells. Then here we can divide the two regions inside of this hill and outside. So W is this potential well is X, that this potential energy is less than D, this term, and X until in this interval X1. So and second potential well is that potential energy is less than D, but other side from bigger than X1, this interval. Then as we know that this problem has it's conserved under motion, so it's and energy is equal to initial energy. Then from here we can see that if initial energy is less than D and our initial condition is lies in this region, then for all the xt for all the time will lie in this potential well in W, because it cannot escape because of this conservation of energy. And also if is initial energy is less than D and the initial condition lies in the V. Okay, here is like this V and this V is potentially messed up, so it's different V's. So then for all the X, all the time X will lie in this term, in this side. So it's kind of some intuitive how to understand for one-dimensional case. So do you have a question here? Okay. Now we can extend this idea to infinite dimensional case. So we for our problem, we have a potential energy GU. It has this following form, and we introduce Nihila functional. It has this following form, and U is from Sobolev space. And we can understand this Nihila functional can be as some extension point of x1 in D. So this Nihila functional helps to get where is this point and where is the D. So some kind of generalization of x1. So we can say that if it's positive, we're in this side. If it's negative, in the side of V. Then depth of potential well is defined by this one. It's infinitum of the potential energy, and U is from the Sobolev space without origin 0, and Nihila function should be 0. So because of here, we need to get 0. So we have here, we can define D here. So also this depth of potential well quantity can be understood as a mountain pass energy or mountain pass level, where we, for example, if we have some valley, and if we pour water into the valley containing local minimum, a region, and as water level is rise in the direction of the potential energy, and it passes at local minimum first from here. So that's why we call it local maximum D. So, or we can say for mountain pass energy. It's this kind of simple example. Now we'll give some properties of the potential wells theory method. First, lemma 1 is about this potential energy. If Fu satisfies our condition H, U is from this class and it is non-zero, then limit of some epsilon 0 with this term, it will be 0. So it can be proved by using this condition. It can be proved from the previous our properties of the nonlinearity. Then if we take a differentiate with respect to this epsilon, we can get our Nihila functional. It is direct computation too. If limit of this epsilon is go to the infinity, plus infinity, then the potential energy goes to minus infinity. It's also direct computation. For it's here we should mention that for case HB we assume that U is positive, and there is some unique point epsilon star, which is a positive. Then by differentiating with respect to the epsilon, and at this epsilon star, it will be 0. So we can see from here too. So it can be proved by supposing there are two roots of equation, this one as epsilon 1 and epsilon 2. Then we, from these terms, we can have this kind of properties that the potential energy will increase in this interval and decrease from in this interval, and take the maximum at the epsilon star. Also, same we have for Nihila functional, which is positive for this interval and negative for this interval. Is negative for this interval, and will be 0 at this maximum. And yeah, it's direct computation too. But and usually then we take this one as a 1 to be easy. Now, using family of potential, we introduce family of potential wells. Will be some omega delta, W delta and V delta. To do that, we need to introduce new form of the Nihila functional with a delta. We just add here delta, and we introduce a depth or potential well is in terms of delta, because will depend on Nihila functional. Then by this lemma, we can divide this space H1 to two regions. First, suppose that Fu satisfies our condition, and from this space we have some radius R, delta R, and some constant A, which is supremum of this term, where this S star, some constant star, is embedding constant from H01 into this L gamma Lebesgue space. And then we can divide this space to the case when is Nihila function is negative and is positive. If U delta is functional, this function will be inside this term in this ball. So in this ball is this ball. So if it's inside, we know we can prove that it is positive. I mean the Nihila function is positive. If Nihila function is negative, then we can prove that it's out of this ball, because it is out of this ball. But if it will be 0, then we can say that it's equal, or some point has this kind of term. But still we have some question how to define inside here and other way. So this lemma about the relationship between this space and Nihila functional. Also, we have the also properties of depth of potential. Well, it has this following form. So it will be bigger than this radius with some constant A. So delta is between this interval where R delta, A delta, A will has this term. So here is dependent on some initial beta and eigenvalue. So it's from previous work, we have this kind of dependence here on domain 2. Second is that it will be, if it close to 0, it will be 0. So there exists some point B, whereas B between this interval, and whereas the DB will be 0 too, and the delta for this inside of this one will be always positive. So it means that we have some kind of beta that will be 0. So this term will giving that there exists some beta. And third one is also obvious, but we would like to mention that is in this interval will be increasing, and from 1 to infinity will be decreasing. So it has a takes maximum, it's 1 here. So this lemma is about depth of the potential well. Lemma 4 is again this how to divide this space, and also we include this potential energy too. So if potential energy is less than our depth, and Nihila function is positive, we can say it is inside this kind of ball with this radius. So we have this kind of radius. Also, if equals 0, we can say this one that it will be inside this ball. Yeah, it's kind of obvious if we draw everything. And we have that if potential energy is less than d and it's bigger than this one from this radius, out of this ball, it's always negative. But still, there is a question how to prove this side, whereas this side, whereas this side, because it's ball. But we still, I'm still thinking how to prove what happened to inside. Maybe it should be negative, but still. So then, using these 3 lemmas, we can give a family of potential wells. So W delta will have this following form. So Nihila function will be always positive, and potential energy less than depth, and they have the origin. And if it's a critical case, we can include this term too. And when this delta is 1, we get just our usual potential wells. Also, we can give this kind of definition to this VW, whereas the Nihila function is negative and the potential energy less than depth. By using previous lemmas, we can prove lemma 5. It's that if delta prime and delta double prime is between this region, and W delta prime, this potential wells is embedded in this form. And otherwise, is if we have less in this interval, then we have for V. We can see from here that if delta prime and delta double prime, so here W with delta double prime is embedded in this small one. So we can see by visualization too. Second, also we have this kind of lemma that if potential energy is between this interval, then we have some delta 1 and delta 2 roots of this equation. Then sign of this Nihila function is unchangeable for delta 1 and delta 2. It's between this. So here delta will be inside of this interval. So it since it will not pass this, if it stays between this one, it will be plus always, and you cannot go to from here from this side to this side, and they cannot change the sign. Or if we have from minus sign here, Nihila function, we cannot have plus, so it doesn't change and go. So we define those as potential wells with their properties to understand inside kitchen. So now using this lemmas, we can prove invariant set and vacuum isolating of solutions. Recall again our total energy. It has this following form. So first is kinetic energy, and we have the potential energy Gu. And then we have this kind of theorem. If U satisfies H and our initial conditions lies in the spaces, assume that some E between 0 and D, then equation that our depths equal to E has two roots, delta 1 and delta 2, is one of them is bigger. Then if all solution of problem with initial energy equal to E belong to W delta for this interval, also we have provided with this one. So all solution should lie in this omega delta with this one. And all solution of problem one with initial energy with equal to E belong to V delta for this interval, with provided this one. So if we have this initial or other ways that where our initial datum lies, so it will stay this region, this is potential wells. You can see from here. So if here is we have E, then we have delta 1, delta 2, and if we have the inside of this one, our energy or initial condition lies in this space. In this side, we will always stay here, or if we have here, it always stay in this region. And also color if assumption, this term will replace by this, then conclusion will be same, also holds. And also using this theorem, we can have that we have some UI, U1, U2, and delta 1, delta 2, the same as in theorem, previous theorem 1. Then for any delta between this interval, both sets W delta and V delta are invariant in both sets in this following form, and invariant respect and the flow of our problem, semilinear wave equation. And our initial energy lie in this interval. Now we'll talk about the vacuum isolating of solution. Note that if initial energy lies in this interval, then we know that this term, this Nihila functional non-zero n was this impossible. We cannot have this kind of. That's why we'll have some vacuum region where there's no solution. So set of all solution problem one with this region with initial energy, there exists some vacuum region UE. So U is from the space and it's not 0, and it will be 0 in between 0. So it is vacuum region. Such there is not any solution problem one, and the vacuum region you become bigger with the decreasing of E. So when it's 0, we have this term has this following form. It will be between 0 and B. So or we can have this kind of donut shape region, like when it's delta 1 and delta 2. In this region, we will not have a solution, any solution for our problem. Now we can So I have little time. So now we can prove global existence and non-existence of solutions. So by definition, we'll give definition of weak solution. U in from this space, and UT from this space, and U is called weak solution of problem 1 in this interval in this space of omega in time from 0 to t, and we write the weak solution in this form for every v from this function this space, and we'll have the U0 from the space. And we should mention U1 here should be, and U1 from L2. Yeah. Then we have theorem for global existence and non-existence of solution. So we have this as usual. Then for problem 1 admits global weak solution if initial energy will less than d and Nihila function is positive, or when it's a critical case, it should be just non-negative. For Blowup solution, it should be this term, and we'll have the for critical case we'll have this term with additional assumption for this kind of assumption for initial condition. So proof is very straightforward, but we use some potential some properties of potential walls method. So if we consider this case is for Blowup with some, for global existence, we construct some approximation solution in this following form. W is some kind of eigenfunction of the H10. Then by using this one, we can get this kind of, by using definition of weak solution, we can have this form by adding some G prime. I mean, prime it's time differentiating with respect to time. We can write, this one is same as writing initial energy in this term. So it we know here from here that it's 0. We have the conservation of law of energy. So we know that from here that it's less than d. Combining this condition, we can obtain the pure estimates for this term, and this term, and this term, which implies that weakly star converge by compactness theorem. Then we can prove global weak solution of problem. For global for Blowup case, we need to show that some norm is go to infinity. So we take L2 norm. So in some time t, you will go to infinity. So here we define some mt. So we will have some derivative with respect to time. First one, second time. Then using conservation of energy, Planck inequality, some convexity and conductivity arguments, and some property of VW, we can establish that this term will be positive. Then we can construct the differential inequality in this following form. Then it will give this term, and we have that some t, which if satisfies this, and it should be Blowup. So if you put this term here, it will go to infinity. So we can prove Blowup. For in both case, critical case, it would be almost same steps with little technical assumption and works. And last, some conclusions that here we get this potential well method and introduce lemma 1 G1 for GU and the lemma 2 is connection between these terms. Lemma 3 is about this depths of potential wells. Lemma 4 is this dividing this Sobolev space. It is also including potential energy, and they're all connected and with this radius. And then by lemma 3 we can have lemma 5 about these embeddings and lemma 6 about sign of the Nihila function. And using these ones, we get invariant sense and vacuum isolating of solution. And using this invariant sense, we can also prove the global solution and blow-up solution. So for future work, we're almost done for potential Wilson method for P Laplacian. So here our initial condition, our condition on nonlinearity will have this term beta, where beta will depend on the first eigenvalue of the P Laplacian, and will apply to the some kind of nonlinear Klein-Gordon equation in this term. So thank you for your attention. Please, if you have some question.
Okay, thank you very much, Bolys, for such a nice talk. So if anybody has question, please unmute yourself and ask Bolys.
Hey, Bolys.
Hi.
Thanks for nice talk. So I have some like very trivial question. So you have a nonlinearity, which looks very general, and then you have some condition on nonlinearity. So what are the, do you have some example which satisfy these kind of conditions?
Yeah, you have just use power P.
So
Yes.
it's power type nonlinearity can be
Yeah, included too. Yeah.
And suppose and logarithmic type or something you cannot here.
I think no. Yeah, it's
Okay.
yeah.
So,
But I think for a logarithmic term, it's possible to construct this kind of potential wells too.
but you cannot do with this method, you mean?
I mean, I think not with this condition.
So potential will depend upon nonlinearity explicitly. Yeah. I mean,
No, it depends on this potential energy, right? It's more dependent on potential energy and how it works. So we can just change other nonlinearities and try to work.
So that means if one consider some general nonlinearity, then still one can do this method. Why are the condition? These conditions are important in your case on app?
Because
maybe I missed something in your.
You mean like more general?
Like because you say logarithmic type also can be done.
I think it's possible to do for general, but when you want to do this kind of inside properties for lemmas, which I introduced, it will be kind of difficult, technically difficult to do this kind of dividing and having this kind of lemmas. And yeah, and I didn't try it, but yeah, it will be interesting to see how it works for different kind of nonlinearities. But I think for logarithmic, it should work. Sure. Yes, there's some.
Thanks. And one more question I have: what are the conditions on domain you have here? Is it smooth or some other condition you need to?
Yeah, it's smooth bounded domain.
Smooth bounded domain. This is the only condition.
Yeah, but here it's possible to do it more for just Rn.
For whole Rn?
Yeah, full Rn.
But you're using compact embedding somehow, right?
Yes, compact.
So for that, for Rn, you mimic that.
Yeah, it doesn't work, but we can use other tricks.
But this method will not work, right?
Yeah, we can use some perturbation method and some conservation laws, because now what we here here, for example, it's kind of, you know, like in most of the RN case, they always assume that initial data is some less than some epsilon, very small, right?
Mhm.
So what they meaning usually is that they lie some close to zero, right? And but they here is more exact point. They giving the exact where should be where the initial condition should be less, or exact quantity for epsilon. For example, you know, most of the results they will give like initial condition should be less than some small epsilon. And yeah, it's kind of this one, but they will exact give some this epsilon, it should be D.
And how they deal with suppose you are dealing with whole domain, right?
Yeah.
Like whole Rn, and then especially like your non-linearity is depend upon first eigenvalue of Laplacian on domain, right?
No, I mean like at that time we cannot have this first eigenvalue because no, we don't have this inequality. So we just drop, we just have a we have the we can have only this with this
This type of only first two conditions, like first term only.
Yeah, but it should be 0 here and 0 here, because we cannot have a beta, because you know, like we cannot
indeed
have the Poincare inequality.
And one more thing, I'm curious, like because you saw when you saw a different kind of literature, different non-linearity, right? Can you go into that slide? And because in some first one there's no sigma, then they add sigma, right? And then in the last paper, Chung, I think, and Korean guys who you tell, here. Here. So in the third one, they add beta and plus sigma, right? So
but they use for heat equation.
Heat, this one is for heat equation.
Yeah, all they use for heat equation, I applied for wave equation.
And here this for heat equation, their method are different, like second and third, or they somehow coincide, somehow strategy are similar.
Can you repeat your question?
For second and third, when they apply this for heat equation,
yes,
the method is similar or is completely different?
No, yeah, it's almost same method, but here we'll have this kind of term which give a dependence of domain.
So the third one was on domain, but
yes, third one is includes this one too. It implies this one.
Okay, so I think second one could be done for Rn. You think so, right? Or sigma depend upon also on domain.
Yeah, it's impossible for these terms to do for Rn.
For whole domain. For whole domain.
Whole domain.
Nice. Thank you, Bolys. Very nice talk.
Okay, thank you, Ritesh, for your questions. There is maybe more questions.
Yes, I have one question. Bolys, nice slides, very nice slides. Thank you for your talk. I have a question about when you are thinking in the conditions on the conditions, your hypothesis, the ones that you call H condition. When you think in this, is because you want to apply later the maximum principle, or which inspired you to consider this?
So we just construct gives this condition to and control this nonlinearity.
Okay.
Yeah, and use this condition, this growth condition, and to control where to see like how it will be and how we. So this one is control in both sides, like can be so much big that we can have.
Okay. So these are the conditions that are appropriate to have the control of the nonlinearity.
Yes.
Okay. Okay, thank you. Just that was my question. Thank you.
Okay, thank you. Anybody has more questions? I want to ask maybe about like the domain. You say it is smooth with boundary.
Yes, most
but-
directly bounded domain.
But it could have like singularities. Maybe it could have like corners or something like that.
No,
It cannot have like
Yeah.
singularities.
no.
Okay, thank you. Please. Well, if no one has more questions, well, thank you very much again, Bolys, for your nice talk.
Yeah.
And then this is the end of the session for the morning, and then we'll have the lunch break, and we will meet again at 2 p.m. in the afternoon for the rest of the talks of this day. So thank you for your attendance, and see you in 2 hours.